Okay, our next speaker are Embedor technologies. So they have X-Node smart sensor as a powerful and versatile wireless sensor platform designed specifically for structural health monitoring applications. So they have trigger accelerometer and 32-bit 3-axis accelerometer that work together, and as excitation is applied to a model structure, the X-Node will automatically detect vibration and seamlessly stitch the data from the two accelerometers starting seconds before the triggering event.
All right, good afternoon, everybody. My name is Kirill Mechitov, and I'm going to tell you a little bit about what we have been doing at Embedor with smart sensors for the monitoring of civil infrastructure. You may have heard the term Internet of Things. What we are focusing on is monitoring of large-scale civil structures. So what we're doing is Internet of very big things. We want to deploy a number of sensors on a structure, and these can be all different kinds of sensors, whether it's an accelerometer, strain gauge, displacement sensor, and collect and aggregate information from the structure from many different points, all synchronized together, and give us insight into the behavior of that structure. Now, what makes these sensors smart is that they're not just capable of collecting data, but also processing and analyzing it, and outputting high-level meaningful information rather than just streams of data. So what we do is collect and synchronize the data, process it and analyze it on site directly in the sensor itself, which is a unit approximately like this, and then send it over for analysis or display to the user. So one big advantage of using wireless sensors is that you don't have to pull wires anywhere. They're typically very fast to install, and that saves a lot on the installation cost and operation costs. So what I'm going to do now is instrument this structure right here with this wireless sensor. Stick it on, flip the switch, and now we have our structure instrumented. It's ready to collect data and send it to this receiver I have right here. Now, if wireless sensors are so great, why aren't they more commonly used for civil infrastructure applications? There are a couple of good reasons for that. One is that for typically a large majority of the wireless sensors that are out there today, they simply don't have the sensitivity for monitoring vibrations in a large-scale structure, such as this bridge in Xiamen, China. Where most of the structural response is going to be below the sensitivity of that sensor. So in order to address that, we have implemented a very high resolution, high sensitivity accelerometer into our wireless sensor node, which is capable of measuring down to fractions of a micro-G for acceleration in such cases. And compared to a wired accelerometer, that high-quality, expensive one that you would use for similar applications, you can get the same or better results with this wireless unit. Now, that's one problem. Another problem is a lot of the applications of civil SHM involve earthquake monitoring and other transient rare events such as impacts. Unfortunately, they don't have the decency to occur on a particular schedule so that we can prepare our data acquisition and be ready when that event happens. That means if you are looking for earthquake monitoring, you have to monitor continuously all the time, 24/7, and that doesn't really work very well with battery-powered wireless sensors. So the typical approach is to use some sort of a triggering device, which is low power, to then enable sensing in response to an event such as an earthquake. So when an event happens, the wake-up accelerometer wakes up first. It wakes up the main sensor, which is higher power, higher fidelity data acquisition, which then collects the data for the device. And this works well enough, but has a critical problem of missing that very first part of the event. So before the sensor has come up, before it has had a chance to initialize, pass some data through the filter, which also loses some fraction of a second, and especially for impacts, that initial impulse is very important, and we don't really want to miss it. So what I'm going to show you today is how we combine some of these capabilities, both high-fidelity sensing and event-triggered sensing, to do it losslessly in a way that we don't lose any data starting from right before the event all the way through the structural response. So what I have here is a sensor that's been attached to a structure, and we're going to simulate what happens to such a sensor during an earthquake. Now, unfortunately, I'm not quite strong enough to shake this entire building, so I'll settle for just pounding on the whiteboard. So this is going to be our earthquake excitation. So the sensor has already detected it. It woke itself up and started collecting data. And now it takes a few seconds for it to send it back to this receiver unit right here. And if I'm able to show you what that looks like. And coming up right now. There it is. So you can see the data record starts from before, some fraction of a second before the original impact when I hit the whiteboard. We set the triggering level of excitation of about 200 milli-Gs. So once that level was exceeded, we're able to collect the data starting from not just that point when the triggering event happened, but a fraction of a second before that, so that you have the full record. So if I can come back to the presentation now, let me show you what that actually does. So here in blue, we have a record of a similar event recorded by a wired accelerometer. And in green is the data record recorded by a wireless accelerometer on the same structure. And you can see the first part, just some fraction of a second, is missing, because that's how long it takes for the wireless accelerometer to wake up from sleep, switch to sensing mode, and collect some meaningful data. So what we do instead is combine it with the data which is stored in the buffer of a low-power trigger accelerometer, which operates continuously even when the main node is asleep and not consuming any meaningful power. And then we stitch it together. We overlay the records together, we synchronize them, we downsample them to the same rate, and we make sure that the resulting data is seamlessly integrated, and you're looking at a single data record. This is all done on the sensor itself, so before it ever goes to the PC, all of the processing is done by the smart sensor. And once it's finished, you can store it both at the sensor for later retrieval and transmit it whenever. So with this, we're able to completely eliminate the loss of data for error event detection and still have very high frequency, very high resolution recording of the entire event, which typically lasts for several minutes after the initial triggering event. So while this unit here is a prototype for this triggering functionality, the X-Node smart sensor on which it is based has been already commercially deployed, including on the world's largest Ferris wheel, which is currently under construction in Dubai. So this wheel is about over 200 meters tall. It has 192 cables, which are kind of like spokes of a bicycle wheel, and each cable is monitored by an X-Node smart sensor, primarily for cable tension. And this system is being deployed right now during the construction phase, and it will continue to operate when the wheel goes into operational phase. All of these sensors are solar powered. They don't need any external wired power. We did run into a number of problems actually implementing that. You would think in the Middle East they get plenty of sun, but unfortunately it's also very hot, and you don't want to charge lithium-ion batteries when it's hot, so we have to schedule it very carefully for safety. And also, again, because of the temperature, we had to make sure to implement a very high precision clock source so that the apparent frequency of sensing does not change with the temperature. With that, we have been able to install and develop the system, and we have also considered some prototypes of this technology beyond the original civil engineering applications because it's quite flexible. It is based around an open source library of data algorithms that can be implemented into the smart sensor. And I know I'm out of time. With that, I will finish, and thank you very much for your attention.